Hello, welcome to another cosmology talk. Today we have Francis Jan Cyr-Racine, who is a professor at the University of New Mexico, and Lloyd Knox, who is a professor at UC Davis. This is a talk actually that was requested by more than one viewer. It's tackling the Hubble tension, which might explain why it's a bit popular, but in a way that feels a little bit less ad hoc than most ways that people try to tackle the Hubble tension. It's talking about a cosmological symmetry and then trying to think of a new physics to exploit this symmetry. And the symmetry leaves almost everything relevant unchanged except for the expansion rate. I'm sure they'll go into more details. Even if you don't believe the new physics that they'll suggest, maybe the symmetry is itself a crucial clue to solving the mystery. Maybe even if you're just looking for systematics, this symmetry might hint at what might be going wrong in the CMB. But in any case, welcome Francis, Jan and Lloyd, and do you want to tell us briefly what you did that is described in the paper?
Well, first of all, that was, except for the raising the possibility of systematics in the CMB at the end, that was an excellent summary. So what we did in the paper, as you mentioned, we discovered this symmetry of many cosmological observables that we were surprised had not been noticed before. In some sense, it's just simple dimensional analysis that these certain dimensionless observables would remain unvariant under a scaling of all the relevant length scales in the problem. But no one had pointed this out, and given that we have these precise measurements in cosmology, it's typically really hard to change the cosmological model and not violate those observational constraints. And so here we found a tool that could allow us to make significant changes and preserve those constraints. And in particular, the way we found to implement the transformation of the symmetry, where we scale up the rates in the problem, led us quite naturally to something that people had said before. Certainly Francis Jan had done his thesis on mirror world dark sector models, where you basically have a copy of the standard model or multiple copies of the standard model that have fairly weak interactions except through gravity with our standard model of particle physics.
So if in a few months people are remembering your talk or your paper and there's only two things that they're able to remember, what would you want those two things to be?
So that there is the symmetry of cosmological observables. You transform the relevant length scales, which are small in number, then these observables don't change. So that's one thing. And then that this insight into the structure of this theory is actually useful for understanding constraints. So parameter estimation, finding constraints on parameters in a model can be quite a black box, right? Where you run your Einstein-Boltzmann equation to make your predictions, you run your Monte Carlo to take into account the constraints from the data and outcome the constraints. And it can be hard to try to understand why the constraints come out the way they do. And I think that this is a useful tool, not only for potentially finding new models, but also for just understanding why constraints turn out the way they do, particularly for light relics.
Okay, so the next question I always ask is, why did you do this? I think in some context here, it's obvious because everyone knows about the Hubble tension and solving it is an important thing. So if you have what you think is an interesting, unique take on why solving the Hubble tension is interesting, feel free to answer it. But otherwise, why this specific method? Why do you think that this symmetry hadn't been written about until now? What was holding people back? And what should we as a cosmology community take away and change?
So first of all, the work really grew out of us. We weren't really trying to directly solve the Hubble constant problem in doing this. And since Francis Jan has a history with mirror world dark sector, it may surprise some people that there was nothing to do with that motivated our work. Actually, what we were interested in is trying to understand constraints on light relics. So trying to build that physical understanding, so you can, again, run this black box, get the constraints on light relics. And certainly the Hubble constant tension was a motivating factor to why we wanted to understand this, because light relics are in principle, a way to solve this Hubble constant problem. But we are mostly, as curiosity driven. We did not understand why, when certain other parameters were opened up, the constraints on light relics remained fairly tight. in the process of trying to understand this, which was at sometimes painful. We spent a long time. We'd come up with ideas, come up with tests for those ideas. The tests would show us we were wrong, and then we finally discovered this symmetry, and then kind of as a test of how our understanding was evolving, we thought, so if we had dark baryons and photons coupled to them, I guess that that would make this problem go away. You're kind of thinking of that as just a confirmation of our understanding. And then we realized, hey, wait, that's actually an interesting idea.
Perhaps the answer to why people hadn't thought of it before is that you weren't coming at it from like, how can I solve the Hubble tension? You kind of stumbled across it and then were like, oh, actually, this might have an impact.
I do remember Lloyd kind of reaching out to me and saying, we got to understand these light relics constraint. And of course, both of us were concerned with the Hubble tension for a while. I mean, I've been thinking about this for some time, but the importance of an effective or the light relic constraint to particle physics is such an important thing that particle phenomenologists always have to work around. Whenever they propose the new models, one of the things, if they study the cosmological history of their models, is that you have to get around these constraints from CMB. So there's such important constraints. And yet, as a cosmologist, and maybe Lloyd the same, I felt I had some heuristic understanding of why or where these constraints were coming from, but not a very deep understanding of what's really constraining in the CMB. Why is it so hard to get a CMB to be consistent with a large amount of relativistic species at early times? And that was really trying, and we as Lloyd said, it was kind of painful sometimes. It was basically a pandemic project. It started in March 2020, I think. So it took a long time, and we have to give credit to Fei Ge, Lloyd's student, that has done a lot of that heavy lifting numerically and tried a lot of hypotheses that led to dead ends and until finally we ended up with something that was promising and seemed to work, and I felt, and probably Lloyd the same, that I finally understood something that I didn't know before. And I think, if you think about the broader context, since these light relic constraints are so important to particle physics, what we found out is that there might be a way to get around those, and suddenly the impact that this realization can have on particle model building can be quite significant, which makes this work, I think, I'm quite excited about this because of this fact, and discussing this with particle phenomenologists and it was surprised that there was this symmetry that was previously unnoticed that could possibly allow to get around some of those relative species constraints.
Enough teasing of exactly how it works. Let's get into the details so that we can see what this symmetry is and how it does free up relic constraints and what the hell that has to do with the Hubble tension.
Okay. So again, I want to give credit to Fei Ge, who has done a lot of the numerical work that we're going to be presenting here, and this paper has been submitted to the archive at the number found here. So as we've alluded many times, so we have the symmetry, but what we found here is a positive potential solution to this Hubble constant. Of course, the first question is, why do we care so much about the Hubble constant in cosmology? Well, that's the meter stick of cosmology. All fundamental scale that we have in cosmology are related to the Hubble constant. So understanding really the value of this constant really tells us about the global scale of the universe. Now, in cosmology, when you do CMB or large-scale structure analysis, what you primarily measures is angles and redshifts on the sky. And these are all dimensionless quantity. In fact, some of these angles are the best measured quantity we have in cosmology. But fundamentally, angles and redshift don't have absolute scales built in. They're dimensionless numbers. They're invariant under an overall rescaling of the whole universe. So if our primary observable in cosmology, things like CMB polarization and temperature and the distribution of galaxies are invariants under this rescaling, then obviously we cannot directly infer the Hubble constant from these measurements. Just because we have this overall kind of rescaling invariance, especially the physics of, or the geometry of similar triangles, if you want. And I'm free to rescale these triangles and keep all the angles invariant. Now, if I were to change my fundamental scales in the universe, things like the Hubble rate, which, as I said, is a meter stick of our universe, so it sets all the scales. If I were to change those Hubble scales by constructions, these angles are all invariant, and primarily for the CMB, this kind of comes out mathematically because all distance in cosmology depends on a specific combination of the Hubble rate, and if you just scale it by some constant factor, so you just rescale this whole universe, all these angles invariant. So we live in a universe where if I take h, the Hubble rate, to f times h, then all the angles in the skies are invariant. So that was kind of our starting point that Lloyd and I had from very early on in this project. But it took us a while to get to the next few things I will say. We got stuck a long time on this point. Why did we get stuck? Well, because there are other length scales in the problem in cosmology. The Hubble scale, which as it says a meter sec, is one scale, but there are other things. Things like the size of fluctuation in the early universe, which we usually describe by the wave number k here, as well as the typical distance between photon scattering events. So photon in the early universe scatter of free electrons, and this distance that these photons travel between scattering event, which is, we can call the mean free path of photon if you want. So that's another distance. And the evolution of cosmological observable depends on all these distances. Now, what we found out is that if you want to have a large Hubble constant, you better rescale the same way all these distances. And in retrospect, it kind of makes sense because it basically, if you do this, it kind of leaves all of these a triangle invariant, if you want. It leaves all the geometry of all these distances invariant. And from the mathematical point of view is that this leaves the equation of motions of everything we know in the early universe invariant. So if you rescale all dimensionful quantity in cosmology. And so basically what we realize is it's basically basic geometry. So cosmological observable have this rescaling invariance because we mostly look at angles and redshift. And on top of this, the evolution of all these fluctuations we see, either density fluctuations or photon temperature fluctuation, only cares about ratios of scales, things like this photon mean free path over the Hubble rate or the wave number of the fluctuation over the Hubble rate. But here, there's nothing really special about cosmology. The statements I'm making here is about basic geometry, which could be valid in a bunch of other physical contexts. And the second statement is really a statement about differential equations if you're solving for different dimensionless variables. So there's nothing special about cosmology, but there's one thing about cosmology that makes the symmetry work, and this is the fact that we live in a special universe where the initial conditions have no intrinsic scale. And of course, cosmologists will say that we live in a universe where we have a power law, a power spectrum of fluctuation. And the nice thing with power laws is they have no intrinsic scale built in. They're the same on every scale. Now, as part of this kind of scaling symmetry we're talking about, or rescaling every length scale in a universe, that means setting a wave number of a fluctuation k to f times k. Since we live in a universe where this ns, or the amount of fluctuation on slightly different scale, is not exactly 1, so if we were just to rescale all the physical length scale of the problem without doing anything to the amplitude of these fluctuation early times, there'll be a little problem. But because we live in a universe with no scale, we can basically reabsorb this change into a change of the overall amplitude of all these fluctuations.
I guess if we knew what the inflation model was, we wouldn't be able to do this because there would be some prediction for what AS is, but in reality we don't, and so we're just changing what the value of our constraint on some inflation model turns out to be.
That's exactly right. And I should say here that since this F is something that rescale the length scale, and we would like to say to increase the Hubble rate by a few percent, maybe 8%, maybe 10%, this scaling is very mild. It's a very mild change, say, on the physics of inflation, if you take this at face value, right?
I guess there's an elephant in the room that I'm assuming you're going to get to because you get to it into the paper, but this is only true for all the ratios, right? But the actual absolute value of, say, the temperature of the CMB also gets rescaled. But I guess just flagging it up that you probably are going to confront that in case people are worried already.
Yes, this is something we will be talking about in a minute.
Absolutely. So we're focusing now on the things that are invariant under this scaling. But yeah, Francis Jan will get shortly to some things that break that symmetry.
And I guess the observations of the Hubble parameter itself has a scale, but that's the whole point. You're wanting to change the value of that.
Exactly, exactly. So using basic geometry and essentially with amounts of dimensional analysis, we came up with this, we call this scaling recipe, so which is a way to essentially get the universe, the CMB, the large-scale structure, and say the late time measurement of the Hubble rate all to agree with each other. And the recipe here is to basically increase the Hubble rate at all time by scaling all the energy density of all the components in the universe by a factor of f squared. So I'm going to scale the amount of dark matter, I'm going to scale the amount of baryons, photon, neutrinos, etc. So that, you know, by the Friedmann equation, everything, the Hubble rate gets larger at every single epoch. So this takes care of boosting the Hubble rate, but as I said, I also have to take care of my other dimensionful length that I also have to rescale. And of course, the important one is the photon mean free path, or its inverse, the photon scattering rate, A/ne sigma t. And if I were to rescale that distance by the same factor of f, so sigma t ne goes to f times sigma t ne, then I leave this ratio, the photon mean free path to the Hubble scale, unchanged. And the third thing I have to do is, of course, is adjust its amplitude fluctuation as I just described.
Just quickly unpack this equation. NEA is the number density of electrons at scale factor A, and sigma t is?
The Thomson cross-section describing the scattering of photons to electron. It's a classical cross-section.
Right, so, but that's something that we can measure in a lab here on Earth.
That is correct. And it depends on the value of the fine structure constant and on the electron mass. So this is the recipe. And if you do that, you get the symmetry that we've been alluding since the beginning of this interview here, which is in scaling symmetry. So if you, at the limit of equilibrium recombination, and I'll come back to that, and massless neutrino, and also come back to that, dimensionless observables are exactly invariant under this symmetry. That is, you know, rho, g rho goes to f squared times g rho, sigma t ne goes to f times sigma t ne, and as goes to as over s, f to the ns minus 1. Now, which observables are invariant under this? Things like CMB temperature and polarization spectra, galaxy clustering, baryon acoustic oscillation, shear power spectra from weak lensing. And by construction, this thing also leaves invariant density ratios. All the omegas that we're familiar from cosmology, things like omega m, omega lambda, invariant basically because we're rescaling the critical density and the density of all the components the same way. So all these density ratio invariant. But of course, that also means we leave things like matter radiation equality invariant, the matter amplitude, matter fluctuation amplitude, things like sigma 8 or S8, whichever combination you prefer, the free streaming fraction of radiation throughout the universe, the baryon-photon ratio, all by construction invariants under this transformation. So this thing leaves a lot of kind of favorite things invariant in cosmology. And this works. You know, if you go to your Boltzmann code, you put this recipe in, as we did here, this leaves these CMB spectra invariants. I'm showing here temperature, polarization, and cross temperature polarization spectra. And the legend here, 1.1, 1.2, refers to different value of the scaling parameter f. So f equals 1, f equals 1.1, f equals 1.2. So 1.2 means I got a Hubble rate that is 20% higher than what I would get for, say, a standard lambda CDM fit to Planck data, for instance. That means, say, 1.2 correspond to an H0 of 81 kilometers per second per megaparsec. And these curves here, I mean, they're really on top of each other. It is an exact symmetry in the limit that I'm fixing the recombination history. Okay, and that's, I know we're going to come back to that. But at least in the land of kind of rainbows and unicorns, where we just do this symmetry by fiat, it works. It is a symmetry of these observables. Now, we have to, of course, we live in the real world. We have to leave the land of rainbows and unicorn and do a reality check. And this is, you know, now we have to bring the point of all the symmetry breaking effect that exists in the real universe. And you already alluded to the big elephant in the room is, of course, that the transformation we introduce here scales it scales up every single densities, including that of the photons. And this is a big problem because we have a precise measurement of the CMB temperature today from Kobe-Firas, and this pins down the abundance of photon today. And since we know exactly how photons evolve cosmologically, it basically pins down the temperature history of the photons. And that's a big problem. So we're not able, technically in the real universe, to just kind of rescale the density of photon by fiat, right? And another important symmetry breaking effect is the fact that recombination is not an equilibrium process in our universe. And that means that it's not invariant under H goes to F times H. Because whenever you get this process that goes out of equilibrium, you get kind of absolute sensitivity to the rate of things happening. So recombination is not invariant under the symmetry and just breaks it. And very similar for Big Bang nucleosynthesis and the setup of the primordial abundance of light elements like helium and deuterium would also not be invariant under such a scaling. And finally, neutrino mass, are not invariant because it's another absolute scales. But of course, this one is easy to handle because you can just rescale neutrino mass by factor f, and then that one can be taken care of. But the three first one I mentioned here are a very big problem. And of course, what we're going to be talking about now is how can we get around those symmetry breaking. So we found something it seems very interesting on paper. We have the symmetry. It gets broken in a big way. Can we get around it?
I guess with this neutrino mass thing, I mean, that again would be a problem if either we had a model that predicted the neutrino mass or we measured it from particle physics. You wouldn't be able to just rescale it. But as we don't have measurements, I mean, it's just a constraint that is a constraint.
That is correct, yes.
Changing the temperature of the photons and the fact that BBN depends on the absolute densities of baryons and blah, 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 is something that I feel like I have a good grasp of. The recombination not being an equilibrium process. I mean, I wouldn't a priori have any idea whether the degree to which it's not an equilibrium process is introducing 0.1%, 1%, 10%, 3,000% size deviations. How big a deal is that point?
A priori, we didn't know. We weren't sure. One thing that we did already know is that recombination happens quite far out of equilibrium. If you look at the ionization fraction as a function of redshift, and you calculate that with the Saha equation, assuming equilibrium, and then you look at the actual full calculation, they're quite different. They're dramatically different. And if you were to calculate CMB power spectra using an equilibrium assumption, they would be dramatically off from what we observe. So that tells us that there is a lot of sensitivity to this departure from equilibrium. And so this means that in principle, we're sensitive to atomic reaction rates that we are, since in our implementation, we're not changing atomic physics, we're not scaling those up. So they will break this symmetry.
I see. In principle, you could just put an F onto all of them as well. But of course, then you'd have to explain why they're different at recombination to in the lab here. I mean, I guess this varying mass of the electron model is one of, I mean, this Hubble Olympics thing did find that was like the best one for explaining the Hubble tension. But I guess, yeah, okay, it might work for cosmology, but then for chemistry, it's a little bit more difficult.
Okay, so given that we have all the symmetry breaking effects, that what seems at face value very hard to get around. I mean, Kobe virus is a big constraint. Now, this is where we're starting to be a bit more going in a more speculative direction, where we say, okay, now we want to exploit this symmetry, not necessarily use it, but exploit it by bringing new physics. And especially what we want to do is get around this Kobe virus constraint on the energy density of the photons. So then the idea was to say, well, technically the symmetry tells us we need to add real photons. Well, instead of doing this, we're going to add dark photons, which is not there's like a million papers written on those, so it's not, we're not just pulling something out of our hat. There's a lot of work on dark photons out there. But the kicker here is that these dark photons, just because we want a successful cosmology, they need to have the same streaming history as the regular photons. So they need to be tightly coupled or very short mean free path at early times. And close to recombination, their mean free path has to increase dramatically, so they basically start streaming, and they behave very similar to normal photon. And one way to do that, of course, is to introduce dark baryons. And by this I mean basically atomic dark matter. You have a dark electron, a dark proton that are ionized at early time, but then form these kind of bound state at later time that are neutral. If the parameters of this atomic dark matter is very similar to that of the standard model, then you can imagine that these dark atoms could form at a similar epoch as normal hydrogen. But that's not enough, because we also need to fix this free streaming fraction, or the ratio of, say, neutrinos to photon in a standard model. Because now we've added these dark photons, but we haven't added anything else. So in order to maintain this free streaming fraction, we need to add dark neutrinos or any other kind of free streaming species. And by the time you've done all of this, then you realize that you basically added a mirror copy of the standard model to your model. And this is a mirror sector. And, if this was just us doing things, that would be a bit crazy. But then you open the literature, especially the particle phenomenology literature, and there's literally hundreds of papers on doing exactly this for other reasons than cosmology. These other reasons include, solving the hierarchy problems and other things. So there's a huge literature already on this mirror sector, which is, of course, interesting. And okay, maybe there's a connection between these things.
The kind of fun question one must want to ask at this point is, are there going to then be dark galaxies, dark stars, dark planets?
Yeah, there should be.
Dark civilizations.
I don't know about civilization, but what I can say here is that all these papers have already been written. Because there's a huge literature on dark star, dark neutron star, exotic compact object, dark disks within galaxies. All of that literature already existed, and we barely hear pointing to it. It's look, this all of this was already out there. We're kind of connecting some dots here, and to me, that makes it a bit more exciting, because suddenly I can connect different areas of physics that, at least at face value, appear not super connected. But yeah, everything you mentioned, there's already a paper on it.
I see. And I guess if they couple to the standard model Higgs, there might be problems from the LHC, but you could probably have a dark Higgs or something as well, and then...
Yeah, so these, I guess I refer on the slides to the twin Higgs. So yeah, in general, these models have two Higgs sectors. There are couples, and in general, these standard models and these mirror sector will interact to some Higgs interaction. There are LHC constraints from that, and this is one of the open question, whether you can actually build this dark sector.
Well, presumably there'd be constraints up from the LHC that might mean it doesn't solve the hierarchy problem, but you could probably just get around that by just having the dark sector produced at a higher energy. It doesn't need to solve the hierarchy problem to solve the Hubble tangent. Maybe it'd be great if it solved both at the same time, but...
Exactly. This is the feedback I got from particle physicists saying, because I was voicing my concerns from LHC constraints on such a scenario, and they were like, well, sure, there are these constraints, but if you don't want to solve the hierarchy problem, then that's fine. This is totally fine, right? So yes. All right. So all these mirror sector ingredient, what they do, they allow you to get all the fluctuation, the gravitational potential evolution more or less unchanged through the universe, so you get a successful CMB. However, what it doesn't do, it doesn't rescale the photon mean free path. In this dark sector, I haven't done anything to the regular photon. So I do need a way to also rescale the very important length scale, which is this photon scattering rate, or this mean free path. And so we found one way of doing this, which was very common in cosmology, and that is changing the primordial helium abundance, which is denoted by Yp, because basically this free electron fraction goes as 1 minus this Yp. And if you were to just send 1 minus Yp to F times 1 minus Yp, then it will effectively implement this rescaling that I need on this photon scattering rate. Now, I should qualify here that this is not the only way I can do that. There are other ways. We already mentioned, say, changing the electron mass, so the variation in the fine structure constant might be another way, or maybe there's other kind of dark sector way of doing this. Now, just for the purpose of this presentation and this paper, this is the simplest thing we could do. Just adjust helium. It's a parameter that's already in all cosmological code. It's something that was easy for us to do.
This changing of the helium fraction, how, yes, as you said, you can just open up your Boltzmann equations and put an F in, but how physically sensible is this? And the constraints from nucleosynthesis, are they wide enough that this is possible, or are you modifying new physics in order to...
Yes, we will come back to that. We have going to show a plot, and this is, of course, a very important, if you want, problem with this.
This is a very good question you're asking. If we did not have the problems associated with this question you were asking, we would be really, really happy.
Okay.
Yes. All right. So we're going to present some results. We're going to try to build the complexity here from plots to plot and try to do it quickly. So the zero test, of course, was just implementing that if this is indeed a symmetry, then if I compare a model to data, I should get some kind of flat posterior because I'm insensitive to this parameter. And this is what this plot is illustrating here. So what I'm doing here, we got this lambda CDM model, the usual 6 parameters. And then we have this plus f, which is literally the scaling parameters that I've been describing, and where we enforce by fiat here all these scalings that we mentioned. We're scaling, of course, the Hubble, but all the densities, as we said, the AS and the photon mean free path. And here we fix the recombination history because, of course, recombination, as I mentioned, is a symmetry breaking effect. So for now, this is the exact symmetry.
And sorry, the adding of the dark sector, it doesn't have to have the same like omega dark baryon. It can have its own.
Right, so we're going to come back to that. Here, basically, you can imagine that for the purpose of this plot, there's basically no dark sector. And this is basically the exact symmetry we described at first, right? I'm just scaling all the densities.
Okay, but also changing the temperature of the CMB,
yes.
But omega dark baryon in principle would then depend on F, I guess, in some way that you would.
Exactly. What's really contrived is the dark baryon to dark photon ratio. And that has to be the same as in the standard model, right? So that has to be the same by the nature of the exploiting the symmetry. All right, so on this plot here, we just show that if I just take this scaling model and I just compare to data, I get more or less a flat posterior on H0 between 67 and 90 here. These are basically the hard boundary that we set because we had to set some range. And just numerical realization of symmetry. I mean, just say, you can fit the CMB and BAO with any value of the Hubble constant if you're actually writing the symmetry.
And this likelihood goes to 0 because of priors.
Priors, exactly.
I was going to ask what the interesting physics was that was happening at the boundary, but okay.
No, here it's just completely prior driven. Now this is a zero test because it's not really a test. It's just saying, we already knew the symmetry was there, so let's just test that our coding works, and it does. All right, now the real test, the first real test was now I'm going to put recombination physics back in. I'm going to let the kind of self-consistent recombination calculation in the presence of this higher Hubble rate, of this, other scaled up quantities. And to our surprise, this is a surprise to me, although I think I have some idea what's going on. This is a very mild breaking effect. So it doesn't, restrict the range of H0 you can fit to the CMB and BAO dramatically. Of course, it does tend to constrain a little bit more the very high value of H0, but this is not a very strong breaking effect. It can still get away with fitting a broad range of Hubble constant to both CMB and BAO. So this was a big surprise, and of course that made this whole adventure that much more interesting. And of course now if you just add the value of the Hubble constant from the Cepheid calibrated distance ladder from Maurice 2021, of course now that picks a value of the, that's consistent with the distance ladder, and essentially eliminates, right, the double tension. It's not alleviated here, it's not all reduced, it's just gone, right? And essentially here by construction, what we've done, we've kind of recalibrated all the distances you infer from the CMB, but calibrated to the distance ladder. That's essentially what you've done here. And of course now there's no boat tension. Of course this is a bit still the land of rainbows and unicorn because we're still enforcing the scaling by fiat. And now what we're going to do is say, okay, now we have this idea how to get around this Scobie fire ass and all this mirror world dark sector, but now we're going to let it be free.
So there's these multiple components we've added, but there's just one additional free parameter here, right? And if you compare this to other attempts to address this Hubble tension, this is dramatically different, right? This has been a hard problem to address. You look at early dark energy solutions, certainly solutions with normal light relics, and you get posteriors. If you don't include the reset measurement as a prior, you get these posteriors that just kind of barely stretch into that region is a typical thing that happens.
Yeah, whereas yours still has a meaningful posterior at 83, so it's substantially widened it. I think I remember having an argument with someone on Twitter a while ago that they were wanting a solution to the Hubble tension to push the central value of the new model to 72, 73-ish, whereas in principle all you need to do is widen it. And I think they disagreed with me that all you have to do is widen it, but I think that's because they had seen what you're describing, Lloyd. Ones that widen the posterior a tiny bit, and 73 is still in the tail. It's just not 5 sigma in the tail. It's 3.5 sigma, and yeah, okay, you alleviated the tension, but with this, like if you genuinely do widen it so that 73 is completely satisfactory, then that is a solution. It's just not it's not predicting that it's 73. It's just saying that it's 73 is as likely as 83, which is as likely as 67. And then Lloyd, your point about there being only one free parameter, I guess the fundamental parameter is an F.
You could take it be the temperature of the dark photons, right? And that would set F.
Yeah. All right, and now we want to kind of open up the floor to say, okay, now we found a way to exploit this dark sector. Now, what if we move away from this symmetry, but we let the data drive all these different parameters which we've introduced now, because we have to add dark photons, we have to add this atomic dark matter component, and we have to add these dark neutrinos, and on top of this we have to let YP be free. So this is what we're doing here in stages. So the green is the thing we've already shown, but now we have expanded it into showing you different parameter combinations. So H0 is still on the x-axis, but now we have this NF, which is the amount of free streaming radiation we have. We have this FADM, which is the amount of atomic dark matter we have as a fraction of the total dark matter. There's the helium abundance YP. And finally, this dark photon temperature is a ratio to the CMB temperature. So the green is what we've already shown you, is the scaling in force, this is the symmetry. And in going from the green to the red to the blue, we're basically now letting all these parameters describing the dark sector be free and let the data really drive the fit. So now in red, we have just CMB, Planck CMB plus BAO. And there's an interesting thing that comes out. Of course, everything gets a bit wider because the model now has more freedom. But the general direction of the red ellipse basically follow the symmetry, or follow, if you want, the green ellipses, which is basically saying that what the data likes, of course, is following the symmetry which we already knew existed, which, is a consistency check if you want, but it was very reassuring to see these ellipses stretch in this direction.
So, sorry, I'm confused about what's been added in the red and the blue, because you say you allow TD, ineffective, and YP to vary, but they're already varying in the green.
Yeah, but in the green, the scaling was in force. So the amount of ineffective we had was basically F squared times 3.046. And ineffective had to be on that value. Of course, there's a little bit of freedom because other things are changing in the chains. And if thing works properly, according to intuition, the red should at least roughly follow the green, because this is the direction where the data should be, or the model should be, invariant compared to the data. And finally, in the blue, we basically add the distance ladder measurement of R21 to kind of pin down a bit better these parameters. And I think from my perspective, if you take this mirror dark sector at face value, there's something interesting that comes out. If you look at the amount of atomic dark matter, is about 3%, plus or minus 1%, which is a very interesting number because it's big enough to have an impact, say, on galaxy formation or having these exotic dark objects we already talked about, but it's not so small that it's unobservable. The temperature of the dark sector is about 70% of that of the CMB, and that's basically the temperature of the neutrino bath today. So that's a very interesting number to be, because we know when the neutrino decouple from the photons, so that might tell you that the dark sector decoupled close to when the normal standard model neutrino decoupled from the plasma. So there's interesting physics there. And effective as some freedom, but it's around 3 or 3.5, so that's also interesting. And of course, the big elephant in the room here, something you brought in earlier here, is the helium fraction. So here I do have in this A21 band in the top right corner, so the A21 here is the direct measurement of the primordial helium abundance from metal pore regions. And we see that comparing the blue contours to this measurement, we are about 3 sigma away from this measurement. So YP, the value of primordial helium abundance you need in order to get a good fit to the cosmological data is low compared to BBN, and it's low by about 3 sigma.
Even with allowing this additional freedom, unfortunately, I guess.
Right.
Yes.
The red and the blue don't fix it for you.
Right. In the sense that the point where 821 intersect the green ellipse is basically lambda CDM. It's kind of the standard, right? But if you want to pull away and write this symmetry, then it forces the photon mean free path to be shorter, and that brings down this.
And sorry to ask, I think exactly the same question as I asked earlier, but the extent of the green one, the fact that it stops is prior dominated. It would otherwise just carry on to...
Yes, because we had a prior on at f equals 1, which is 67 and something here, all the way to 1.25, I believe, 1.3, which is more than 90 kilometers per second. So it's the green here is completely prior driven, yes.
The low end of that prior at f equals 1, though, is very physically motivated in that Phi-Ras sees as many photons as Phi-Ras sees. We can't subtract them.
Yeah. You could look at the constraints for f of 0.9, but then the physics that would be producing that is a very... Talk about rainbows and unicorns.
Yeah.
Yes.
Right. I was saying earlier how cool it would be if the omega dark baryons was equal to omega baryons, but I guess the fraction in matter of the baryons is like 25% or something, wouldn't it? So they'd be up at 0.25 on this plot. So yeah, you are looking at a very different fraction, unfortunately.
So, and it just comes from the scaling, right? The dark baryons are about 8% of the light baryons, right? Because the Hubble constant's high by 8% from rescaling.
I guess the next question is, what comes next in terms of where does this lead us to? I guess YP is the biggest elephant remaining in the room, perhaps. But what else? What other models other than a dark sector might be interesting and might tackle this YP at the same time? I noticed that in my intro, I was mentioning that your rescaling symmetry might help someone look for systematics, and Lloyd seemed a bit skeptical about that. Maybe it was just because of I should be more optimistic about new physics, but maybe there was some physics reason why this won't help look for systematics.
Well, you particularly mentioned systematics in this CMB data. So that's what I was objecting to, because there's just no way that the Hubble constant problem can be reconciled as unidentified systematic errors in CMB measurements, because you can achieve this prediction of a Hubble constant of 67, 68 from, tell me what CMB data set I should throw out, and you still get it.
Yeah, I know what you mean. I mean, you can even do it with BAO and nucleosynthesis alone.
Right.
I guess there could be some common systematic, which is this rescaling that is then the same way that if there was a dark sector, there's some common new physics that's affecting all of them the same. There could be some common systematic, was I guess what I was thinking.
I guess in principle. But that's independent. These are completely independent experiments, observing the sky at different times, using different frequencies.
So I'm going to go through a few points, and then Lloyd has a few more you probably want to discuss. And I think that again, the biggest elephant in the room, and the thing that will, if anything, break this whole ideas and symmetry is whether we can achieve this higher photon scattering rate while maintaining consistency with Big Bang nucleosynthesis and the primordial helium abundance. Can we find a way to do this? Maybe there's some ideas out there. So this is the biggest question. And then there's other more specific thing about the presence of the dark sector, which are more exciting if you want. Things like, now this thing predicts a 3% of abundance or so of atomic dark matter. This has interesting consequences for structure formation, galaxy formation, exotic compact objects. This is kind of exciting. And again, there's a lot of papers on that. There's the particle physics model building. Can you build this dark sector? And the question, I think the answer to that is yes, because there's already papers doing that out there, motivated by this work, which is of course very cool. And one question we got right away is how nonlinear evolution, of course on a very small scale, break the symmetry. It could be used to distinguish some of the ideas we have here, and that's largely unexplored so far.
One question is, I don't think is. Anyway, I'm not sure how keen I am about it, but there's a question: is low helium really possible or not? And the measurements. I think that my impression of the measurements is that they're pretty solid, and so to reconcile, you'd have to have some very early stellar population that produced more helium, right, than there was during recombination. That still leaves the question of what's happening with Big Bang nucleosynthesis. Can you So I think that helium. I hope somebody, somebody picks this up and works on it. But I don't. It doesn't seem like a very likely way to go, especially when the end of the day is you get the helium amount. You need to get the helium amount that agrees with the standard model, right? So. But anyway, there's still questions there. I'm really excited about Cliff Burgess is working on a paper that, for entirely different reasons, where he has ratios of masses changing over cosmic time. So anyways, this is another way of changing the scattering rate potentially, because you would change the Thomson cross-section.
He would still need the mirror dark sector?
We would still need a mirror dark sector. One other question is, okay, with current data, we can't distinguish these effects of out-of-equilibrium recombination. But what would it take, right? So with higher resolution, lower noise data, with the CMB alone, could you actually rule out or kind of confirm that, yes, we I think that another thing is it's just exploring the constraints on atomic dark matter parameters. We haven't opened up all of that. Even in what we looked at there in the paper, one of the questions is, well, do you need the binding energy of the dark atoms over the temperature of the dark photons? Do you really? We just fixed that to be the same as in the light sector. But we probably order. This is important for model building, right? Do you really need that to be the same, or how much freedom is in that?
And I guess there is then hope that in some way the dark sector is different in just the right way, that it's not needing this change to the helium fraction, so that you don't have to introduce some other new physics. It's just that the new physics you're already introducing is not quite identical.
Oh, that's a good idea. I actually hadn't thought of that. That's a very good idea.
So what work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
I mean, one thing that kind of worries me at the moment, kind of related to this Hubble tension, is this local asymmetry in supernova, and this debate that goes back and forth between some people and some other people, and I read papers and I read counter papers, and it doesn't seem to be settled, and everyone to some extent has good argument, and I don't know what to take of that, but that worries me. That as much as I'm super excited about the symmetry, that we found a way to get a large Hubble constant with some problems, but with the CMB and all, I'm still worried that there's something going on in the local measurement and that we're not paying sufficiently attention to. So I'm a bit worried about that. I've been reading a lot of papers and try to make my mind about this. But of course, I'm excited about CMB and symmetry, so I'll keep working on that.
One of the recent talks by Asta Heinerson and Haley McPherson was on that exact topic. They weren't looking on the observational side, but on the simulating side. And if you take into account the full inhomogeneity, how much does the potentially measured Hubble parameter change? So people should check that talk out if they also are concerned by this. Thank you everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified. If you have any questions or suggestions, please leave a comment. And thanks, Francis, Jan, and Lloyd, for the great talk.
Thank you, Sean. It was fun.
Thanks for having us. Yes.